Script. Hey everyone and welcome. Today we're tackling a fun but tricky tree problem from Leetcode. It involves splitting a tree apart and working with XOR values. It might sound intimidating, but we'll break it down step by step. Let's get started. Script. Alright, here's the mission. We're given a tree which is just a bunch of nodes connected by edges with no cycles. Each node has a number associated with it. Our job is to remove exactly 2 different edges from this tree. Script. When we snip 2 edges, the tree falls apart into 3 separate pieces, or components. For each piece, we need to calculate its XOR sum. That just means we take all the numbers on the nodes in that piece, and XOR them all together. Once we have our 3 XOR sums, we find the biggest one and the smallest one, and subtract them. That difference is our score. We want to find the 2 cuts that make this score as small as possible. The script. Before we dive into the code, let's quickly remember a super useful property of the XOR operation. If you XOR a number with something, and then XOR it with that same something again, you get the original number back. This is a fantastic shortcut. If we know the total XOR sum of the entire tree, and we figure out the XOR sums for 2 of our 3 pieces, we don't need to recalculate the third one. We can find it instantly just by XO. Ring the total with the 2 parts we already know. This will save us a lot of work. Script. Let's walk through the example from the problem. Suppose we decide to cut the edge connecting node 0 and node 1, and the edge connecting node 1 and node 2. This breaks the tree into 3 pieces. The first is just node 0 by itself, so its XOR sum is its value, 1. The second piece is node 2 by itself, with an XOR sum of 5. The third piece is everything else, nodes 1, 3, and 4, all still connected. Their values are 5, 4, and 11. If we XOR those together we get 10. So our 3 component values are 1, 5 and 10. The largest is 10, the smallest is 1. The score is 10 minus 1, which is 9. Our goal is to find if there's a different pair of cuts that gives an even smaller score. Script. Okay, so how do we find the best cuts? The most straightforward way is to just try everything. This is a classic brute force strategy. We can pick our first edge to cut. This immediately separates one subtree from the rest of the tree. Now we have 2 pieces. We still need to make one more cut in that larger, everything else piece. So for our first chosen cut, we can then explore all possible second cuts in the remaining part of the tree. For each complete set of 3 components, we'll calculate the score and keep track of the minimum we find. The editorial calls this a Double DFS approach. Script. Here's the Python code for that Double DFS strategy. It might look a little complicated with multiple functions, but we'll walk through each part. The key is that there's one DFS to gather initial info, and a second, nested DFS to test the second cut. Script. The first step is a standard depth-first search, which we'll call DFS1. Its only job is to gather some basic facts about our tree. As it visits each node, it calculates the total XOR sum of all the nodes in the subtree below it. It stores these values in an array we'll call XOR sum. It also keeps track of each node's parent, which will be useful later. Script. Now for the second function, DFS2. This function does the heavy lifting. We call it after we've already decided on our first cut. The value of that first cutoff component, which we call XOR1, is passed into this function. As DFS2 traverses the remaining part of the tree, it pretends to make the second cut above every node it visits. For each of these potential second cuts, it calculates the 3 component values, computes the score, and updates our minimum answer if this score is better. Script. Finally, the main loop brings it all together. It iterates through every node, from 1 to n-1. For each node, it pretends we're cutting the edge right above it. This gives us our first component. Then, it temporarily removes that edge from our tree structure and calls DFS2 to explore all the possible second cuts on what's left. After DFS2 finishes, we add the edge back, so the tree is whole again for the next iteration of the loop. It's a clean way to test every combination. Script. Now let's look at the second approach. It's a bit more elegant and relies on a common and powerful tree trick. The goal is the same, check all pairs of cuts, but it does it more systematically. First, we run a single DFS to gather data. We get the subtree XOR sums like before, but we also record in and out times for each node. Think of these as timestamps for when we first discover a node, and when we're done with it. These timestamps allow us to instantly check if one node is an ancestor of another. With this info, we can just loop through all pairs of nodes, and for each pair, we'll know exactly how the tree splits apart. And script. And here's the code for the second approach. You can see the initial DFS function that gathers all the data, including the in and out times. Afterwards, there are two simple nested loops that iterate through all the pairs of nodes to test the cuts. Let's look at the pieces. Script. The core of this method is its single DFS function. As it walks the tree, it does three jobs. First, it calculates the XOR sum of the subtree, just like before. Second, it records the current value of a global timer into the in-time array for that node. Then, after visiting all children, it records the timer's value again into the out-time array. Script. After that one-time DFS, the rest of the work is straightforward. We use two nested loops to create every unique pair of nodes, I and j. For each pair, we use our fastAsAncestor helper function. There are three possibilities. If I is an ancestor of j for is, we use one set of formulas to find the three-component XORs. If j is an ancestor of I, we use another. And if they're in different branches, we use a third. In all cases, once we have the three values, we calculate the score and update our minimum. The script. So how do these two approaches stack up? In terms of performance, they are actually the same. Both have a time complexity of big O of n squared. This happens because they both, in their own way, have to consider every pair of possible cuts. The space required is big O of n, mostly to store the tree and the arrays for our pre-computed data. For the typical constraints on a problem like this, an n-squared solution is perfectly acceptable. Script. So to wrap things up, we explored two great methods for solving this problem. The first, a double DFS, is a very direct and intuitive way to think about making a first cut, then a second cut. The second approach was a bit more refined, using a single pre-computation step with in and out times to make checking all the pairs very clean. The biggest lesson is how understanding simple properties of operations like XOR can unlock elegant solutions. Script. I hope that breakdown made sense and helped you see how to approach these kinds of tree problems. If it did, please hit that like button and maybe subscribe for more explanations. If you have any questions or a different way of solving it, I'd love to see it in the comments. Thanks for your time, keep coding, and I'll see you in the next one.